Hi everyone, to another exciting lecture on research methods. We are talking this time about inferential statistics and the results that you gain through your data collection and the tests that you do on that data. With inferential statistics coming from the idea of descriptive statistics, we're not just summarizing and explaining what we found here, we are actually testing hypotheses, those predictions that we have related to the interworkings of independent and dependent variables or other variables that you're investigating relationships between. So this is the real sort of meat and potatoes of making science, right? The real questions being answered, if you will. So there's some ins and outs we need to go through with that, and then a couple of the things that could go wrong along the process, right? So first of all, inferential statistics, of course, this is just what we can infer, we say, given the data that we collected, right? So that survey data, the experimental data that you gathered, that all means something, and hopefully those hypotheses are supported. But even if they're not, they give us some sort of information here, right? So the goal here is to test our predictions to see if our ideas are beyond chance, maybe supported by that data. And then sort of the degree beyond chance, the p less than number, is sort of the strength of that conclusion, right? Sort of the nature of the statistical significance testing sort of implies that the more significant the result, the less likely these results are just happening by some sort of chance, roll of the dice, or random relationship between variables. So that's sort of p-value, and of course the other statistics we get, the f values that we get with ANOVAs, for example, the larger the f value will then usually dictate, along with other things in the equations, the value of the p-value, the probability that that size f was obtained by chance alone and not due to the systematic differences that you're hypothesizing are at play here. So in graphical form here, right, we're taking individuals from some sample in our studies, whether that's a correlational study, qualitative study, where you're coding individuals in an environment. You're still taking samples from some sort of larger population to investigate, and then you're testing your data. You're coming up with your results sections based on that sample, right? So the conclusions that you come up with are based on that sample, and then the inference you make is back to that population. So that's why generalizability and all of those things are so important, because the sample that we get maybe has some significant results doesn't mean that the larger population maybe would react in the same way, would have similar relationships between thought patterns, that sort of thing, or would react to our manipulations in the same way. So going through some of these hypotheses or predictions that you might have, right? Remember, there's two types of hypotheses. We usually focus on the experimental, right? And I don't ask you to put the null hypotheses in any formal sort of way in the individual proposal or final group project. But the null is the assumption there's no relationship or no difference, right? Based on some sort of intervention. The experimental hypothesis is that that intervention, relationship, difference would exist, right? And we say beyond chance, right? So an experimental hypothesis is the expected direction or strength of that relationship, generally between two or more variables. Sometimes you can have interactions or stuff like we talked about before. So an example of something like that I like to look at is sort of hypotheses related to maybe areas that you eat around campus when we're able to be on campus, or maybe political elections, things like that, right? There's a lot of statistics and sometimes popular media likes to talk about these things. So a hypothesis you might have related to, let's say, eateries is you are significantly more likely to get sick after eating at the Nugget, maybe versus other eateries on campus, or some comparison there, right? And maybe you see some statistics, some descriptive statistics, like 47% of people who eat at the Nugget get sick, right? So maybe you're comparing that against other percentages. Maybe you ask people ratings of their feelings, but you use some statistics to sort of compare, to test that hypothesis, right? Similarly, you might have a hypothesis related to maybe politics, chances of political people winning or not winning. You can look at a statistic like that and say, okay, 52% are on this side, but then remember they always present these with margins of error. So these are interesting and used in statistical testing. Sometimes we don't talk about a lot with things like confidence intervals, which some statisticians actually say are better ways of assessing statistical significance and differences that might exist out there. So in this case, 52% plus or minus 3% would mean that really either candidate has a chance of winning in this case. So another example of that, the null hypothesis in that first case would be that there's no difference, right? The mean number, let's say, of individuals, if we're looking at a count, let's say, ill after eating at the Nugget will be equal to the number ill after eating at other local restaurants, right? If you want to do an experimental hypothesis, what we usually see in journal articles and what I would want you to produce, would say something like the mean number of individuals ill after eating at the Nugget will be significantly higher than those individuals eating at other local eateries, right? So very clearly you're comparing the IV there, the Nugget versus other eateries, and the DV there is how ill they feel, right? Or the number of people reporting illness. There's a lot of different ways you can measure that, right? And then what you look at in this case is maybe the mean numbers, right, of people being sick. So if the null hypothesis is true, that there's no difference, the means would look fairly similar, like we have there, 4.6, 4.5, something like that. But if your hypothesis is supported, right, it would probably look something like 4.6 versus 1.5, right? The mean number for the patrons at the Nugget feeling sick is much higher there. In reality, it might be 4.6 versus 4.0, something a little bit more subtle like that. And that's why statistical significance testing is important, to show that that subtle difference is actually meaningful given the number of people we sampled and the error associated with these measurement devices, all of those things that matter, right? So that probability that we use there to test is, probability significance testing, right? So our significance testing is based on what we call sort of these probabilities of p less than 0.05, p less than 0.10, which really just represents levels of chance that we're willing to take, right? So it's the chance that we would obtain two means, a correlation of this size, whatever your statistic is, by chance alone, right? So it's the probabilities. We're using, like I said, these p-values, which is just representing chance, right? So 5% chance is the p less than 0.05, 1% is p equals 0.01, so any value less than 0.05 or less than 0.01 would be significant, quote unquote. If you can see me, I would be doing the air quotes, right? But that, again, does not necessarily mean, everything. It's taken in context, right? For example, if you have a huge sample size, many correlations that are not very large or maybe meaningful may come out and be statistically significant. So again, you have to take these very cautiously and recognize that there's a larger sort of relationship between the sampling that you do, the individuals within the studies, the probability of obtaining significance, So again, sample size matters there. Larger, of course, will dictate likelihood of getting significance. And then the sampling distributions, of course, across different samples that are taken. So when you look at, let's say, mean values across groups, or correlations between variables across different samples taken at different times, there's sort of interesting patterns that can emerge there. So when we do this significance testing, there's a few different things that can happen, right? And we talked about this briefly with the type 1 versus type 2, and this is a larger sort of depiction of that, where we're looking at reality versus the decision that we make in the laboratory or with our results, wherever you're calculating that in your home computer. And in this case, it's looking at the null versus the rejection of that null hypothesis, i.e. accepting the experimental hypothesis. So in reality, if the null is true, there's no relationship, and we retain the null, right? So we say, okay, the null is true in our decision that we make there on the left-hand column. That's a correct decision, right? However, if the null is true in reality, right, and we reject the null and say that there's a difference, in means or a sizable correlation that we should be paying attention to, that's when we're making that type 1 error, right? The opposite of that, right, when we retain the null, right, when we say there's no difference, but in reality there is a relationship there, or there is some sort of effect of that independent variable on that dependent variable, and your study was just not able to capture that, that's the type 2 error, right, where you're not saying there's a significant difference or a significant correlation, when in reality there is a relationship there, and because of sample size or unreliability of measures or something like that, your study didn't capture that. Of course, if the null is false and you reject the null, that's also a correct decision. We call that power because that is the power your study has to find a significant difference when it does truly exist, right? So that's the power of your study. Very intuitive, intuitively named there. If your study is high power, you are likely to find significant differences when you should, right? When you should reject that null, you actually do. The most important ones there, i.e. test material, is the type 1 error and type 2 error as well, right? So type 1, saying there's significance when there shouldn't be, there's not in reality, and type 2, not finding that difference when it really is there somewhere, and you didn't find it. Which I should note that the latter, the type 2, is most likely what y'all will run into in your studies because you have low sample size and sometimes lower reliability measures, not necessarily by your fault, right? But the type 1, of course, is the sort of more egregious one because that's saying that you're making science, if you will, when really no science should really be made. There's nothing of significance there. So your significance levels that you choose kind of are, related to these. You don't really want to do that type 1 error, so we make these conservative p-values, p less than 0.05. If you have a lot of participants, maybe p less than 0.01, so we don't say that it's significant when it's not, right? If you're afraid of the type 2 error, not find a difference, then that's when maybe you might accept a p less than 0.10, right? 10% chance. But traditionally that 0.05 is the 1 in 20 chance is the typical cutoff, and again, 0.01, 0.001 would be even more conservative. So in that case, more likely to make a type 2 error, less likely to make a type 1 error. With 0.05, that 1 in 20 chance, a p-value of 0.05, so any correlation, any f-value that's significant at the 0.05 level, you're more likely to make a type 1 error, right? So say that there's a difference when there's not one versus the type 2, right? Hopefully you can capture those differences and you don't miss them, so you don't make any type 2 errors with a 0.10 or 0.05 significance level. 0.001, 1 in 1,000 chance that you'd find this result by chance alone, that conservative of a significance level, you're more likely, again, to make that type 2 error. Anyways, the marginally significant just means that you're beyond that significance level, right? So sometimes if you have 0.06, 0.07, people say, well, that's not meeting that 0.05 significance level, so it's marginally significant. And I've been tempted to use that language myself if it's 0.07, 0.08, and I know the pattern is emerging, but it's not quite there. It's a good time then to just collect more data, and to see, maybe if your manipulation's not strong enough. That's why people do pilot studies, to make sure these manipulations are strong enough, to make sure that, they're set up to find success here. But the more you sort of investigate through pilot studies, the less you're saying it's the actual sort of run of the study, the more sort of questionable that becomes. You don't want to necessarily set yourself up for success to the point where you're not doing science anymore, right? If you know the result, it's not scientific anymore. And the tests we use for these, we use t-tests, f-tests, and all this to sort of get these values that then we look at in terms of this p-value, right? So you run a t-test between two means, where you're looking at the between group difference between the two groups, let's say getting an intervention and not getting an intervention, divided by their within group. And this is more for your stats classes, but know that it's just looking at sort of patterns that emerge because of the intervention, because of the variable that you're speaking of, right? And it's beyond chance or beyond individual differences, which is what that within group variance is kind of capturing, right? The sort of random fluctuations between groups, or within, each group itself, how variable the people are in general. Anyway, so, f-tests are a little bit stronger because you can use multiple IVs or multiple levels of IVs. So usually ANOVAs are used if you have a 2x2 sort of experimental design or something like that. We also have correlations and regressions, of course. those, the significance is tested on the size of the correlation. So the further away from 0 towards 1 or -1. In social sciences, we say like 0.1 to 0.3 is low, 0.3 to 0.4, 0.5 is medium, and above 0.5 is large correlations. So those generally are significant. Anything above 0.3, 0.4. If it's not significant, that means it's probably a sample size issue, and it's a type 2 error, right? Regression, same thing. You test what's the beta weight or the B weight in that case, but it's similar to a correlation. And the larger it is, the more likely you are to have a significant B weight or beta weight, and your IV is significantly predicting that dependent variable. So with ANOVAs, we get an F, and the larger that F, again, the more likely it is to be significant. Correlations, it's an R, and regressions, it's either a B or a beta that you get, and that B or a beta is tested for significance. Of course, your p-value, then the smaller the p-value, the less likely that F or R or B was that size by chance alone, right? And of course, error is taken into account there in terms of calculating that p-value. The error in different sorts of equations is modeled differently, but it's important in each type. I mentioned confidence intervals earlier. What those sort of relate to is less of a cutoff and more of a range, right? So you might say that the correlation is significant if you're using traditional p-values beyond, let's say 0.05, or now with the computers, it'll say p equals exactly 0.043 or something. So you have exactly a 0.043 or a 4.3% chance that you got that F or R or B by chance alone. Confidence intervals will say that you have a 95% chance that your correlation, let's say, is between 0.25 and 0.35. So it's saying, 95% chance it's between 0.25 and 0.35, but we don't know exactly what it is. So a little bit more leeway there and a little bit more honesty in the reporting. So when you obtain the significance, when you calculate your R's or F, you'll get some sort of alpha size. It'll say again P equals something now, and you'll put that exact P value in there. That is obtained and calculated partially on the sample size of your experiment or survey that you run, and is of course dictated by the size of the effect that you see of that IV on that DV, or that independent variable and the dependent variable in a regression equation, or just the size or the degree of overlap between those variables in a correlational sense. Any correlation is basically a representation of the effect size of those two variables affecting each other, right? So if you look at the correlation between anxiety and performance or whatever, the correlation between anxiety and performance is an index of that effect size. So that will dictate how significant your result is, right? Now, the larger question that needs to be asked is, what does the presence or lack of that significance really mean for your study in particular, right? In some cases, it's not actually a horrible thing. If you're looking at some sort of negative effect of a situation in a program, like my honors thesis, I looked at a caseworker turnover on families dropping out of a home intervention program. The caseworker turnover is somewhat unavoidable. So seeing that there was no correlation there and no effect was actually helpful for the organization. So that was actually a good thing. It can be interpreted in different ways, but usually journals want to publish significant stuff. So if you don't get significance, one thing you need to ask yourself is why, right? So sometimes studies can, lack instructions. If it's a survey or even an experimental sense, they could come into a lab study and not know exactly what they're supposed to be doing. So something about that could have happened. If it's an experimental study and you didn't do pilot studies, the manipulations could be weak. They may not have worked, and so all the data you collected may just turn into a pilot study. But you need to improve those manipulations, make the sort of videos more harsh for the aggressive video condition or whatever. And whatever measurement devices you could have used could be unreliable, could have items that are not working for the certain sample you're using. So going through item by item is sometimes important to see exactly what happened with that measurement scale. and looking at the data. We say eyeballing the data, right? When you get that data, we say it's important to look at it also because if there are oddities in there, if people were skipping items or answering items all the same way or something, that can be problematic for your statistics. So we say to eyeball your data, to look at the frequencies or any descriptives that could maybe point to outliers or things like that. You can look at the range of scores. So if it's only a 1 to 5 scale and somebody puts a 6 or a 7, obviously you need to dig in there and see if other people did that or why they might have done that, or maybe just eliminating those answers. That happens a lot on paper and pencil studies, not so much in electronic means anymore, because you can restrict what they actually click in that case. But you can still have outliers and missing data and that sort of stuff, even at the scale level. So it's not necessarily at the item level, but if someone scores 100 out of 100 on an anxiety scale, and the mean is 50, they could be an outlier, and you could have a rationale for throwing that person out, because they could be messing up your data. Finally, of course, you want to look at the sort of various things that could go into your sample. Right, so we talk about probability being a huge sort of result, or the probability of you getting significance being a result of the sample that you get, right? Not only the variability that they express when they answer questions, but the diversity and the size of people, frankly. If you get enough people, you typically tend to have significant results. Across different studies, you'll see different means, different standard deviations, and things like that. And that's what we call more the standard, the sampling distributions, right? So the more samples you do, the more accurately you will obtain that population mean, of course. So sample size is important. The power of your study is directly related to this. So the more power you have, the more likely you are to find that significant result when it's out there, right? So look for those. But also you can get those erroneous findings that are related to sample sizes being so large that correlations can emerge. One of my thesis students wanted to look at ethnicity and job satisfaction because it came out significant on the correlation matrix, but ethnicity is not scored in a meaningful way. It's categories. So you can't look at categories, especially more than 2. You can sort of fake it with 2. I said in an earlier lecture, but if you have more than 2 categories, correlations don't really make sense. So you got to be careful that not only is this measurement scale accurately represented and makes sense with the correlations, but then also it's not something you're just trying to capitalize that wasn't hypothesized, right? Anyways, these implications of your studies are limited to all sorts of things related to your study, right? So when you make that final leap back to the population, your data itself is, the quality of that data, I should say, is important, right? So if you have scales that are unreliable, data that seems misleading, the implications you can draw from that are very limited, right? You'll see also that sometimes, people that sort of are aware of the types of stats that should be used in certain contexts are not appropriate. They may not be throwing out outliers that they should, that sort of thing. So those sort of things should be watched in terms of the appropriateness of the statistics being used, as well as sort of the measurement scale sort of issues that I discussed earlier. And then finally, when you're making these implications, the generalizability is important. So the demographics and things like that have to be representative of the people that you want to look at eventually, or make these assumptions about. So you have to take into account, do you have sort of the representations of, let's say, a population, as the example below shows, or is your sample sort of biased based on who you could find? That can be very important to then the generalizability, of course. Hopefully this makes sense, and hopefully these sorts of results can then be incorporated into your individual studies once you create the group project, and then look to see what your results will say.